Hello everyone. So this is class tonight. We unfortunately are not able to meet because I am hosting a conference. Literally as we speak, I've been running around campus all day trying to get this together, but I still made time for you all because you all are special to me. So that's good. So tonight we are gonna essentially be covering chapter 3, which deals with logic. Now, logic is something very interesting because when you think about logic, you might be thinking about, how things make sense, right? So if someone has good logic, we would say that a lot of the points they're making are valid and that they have great points that they bring up, right? Or they have good reasoning skills. And that's essentially what we are practicing. Let me turn this on silent. I've been getting emails all day. But essentially what we are doing is we are learning the mathematics behind reasoning. So we're going to be learning what makes a good argument. And what we're going to learn is that an argument is not something that you have on Twitter. An argument is something that you use to bring up your point across and if it's valid or not. And so we're going to learn how to check mathematically if the words I'm saying make sense, or if the conclusion logically follows the premise. And this stuff gets really fun because this opens the door to understanding things like contradictions, or how you know that someone is using a fallacy. And what that means is that, like, if someone uses a fallacy, then their premise, their conclusion doesn't follow from their premise. Or they're using techniques that we know shouldn't make our opinion, right? So we could say the president is, the president, we shouldn't listen to him because he's stupid, okay? Well, that's called an ad hominem. Whether you think the president is stupid or not doesn't necessarily mean that you shouldn't listen to him, right? Whoever the president just so happens to be at the current moment. So that's an example of an ad hominem. Another one is a red herring, which, someone brings up something completely off the wall to try and distract you from your main point, right? So there's a lot of fallacies out there that unfortunately won't have time to get into, but we will be talking about arguments. So here's our slides. So if I can turn this on, does this work? It does. So we are going to be talking about first quantifiers. I might just use this to help me out. So, for dozens of years, surveys done by marketing companies have shown that primary concern for a majority of American women is taking care of their families. So it's no coincidence that a lot of the household products that are traditionally bought by women are advertised in a way that plays on that concern. The implication, sometimes overt and sometimes subconscious, is that if you're a good mom that cares about your family, then you'll buy this particular product. This is easy to say that people can't possibly fall for, since it's blatant, it's easy to say that, but there's all the evidence you need that it works. Advertisers keep doing it. This is exactly why the sort of mind control that we talked about we didn't talk about that, but there's a lot of techniques we can use to persuade someone, right? Oftentimes through our words. So we're going to end the arguments we make. So we're going to talk about statements, okay? And we're going to fight back from people manipulating us by studying symbolic logic, which uses letters to represent statements and special symbols to represent words like and, or, and not. And this will allow us to remove our emotional bias from an argument so that we can analytically evaluate the logic behind it. So oftentimes when I'm speaking, because we are emotional creatures, right, I can say something. Let's do this, right? The president is stupid, all right? That's a words that I said, right? And people, because politics is crazy right now, right? People get a lot of emotion with that. Either you're very happy that I said, yeah, you're happy that I said, yes, you're right, the president is stupid. Or you're like, no, the president's not stupid, right? So a lot of emotion behind those. So what logic tries to do, the study of formal logic tries to tear down all the emotion behind our words and just looks at, are they factually correct? Do they make logical sense? All right. So that's what we try to do. So we got to first start by statements. In the English language, there are many types of sentences. A few of them are a factual statement, right? You have to pass the bar to practice law. Commands, get out of my face. Opinion, strawberry cheesecake is the best dessert ever, which it is. Questions, sup with you, and exclamations like holy cow. In the objective study of logic, we will only use factual statements. We want to study only factual statements. And it's pretty hard to decide if get out of my face is true or false, right? So a statement is a declarative sentence that can be objectively determined to be true or false. So a statement is either always true or always false. It's either true or false, no in between. It cannot be both true and false. So we're going to look at some phrases and determine whether they are statements or not. Okay? So, most scientists agree that global warming is a threat to the environment. So when you want to see, like, is that a statement that can be true or false? Well, most scientists, they can decide whether global warming is a threat to the environment or not, right? So that is a statement. Okay? Statement. All right? Is that your laptop? That ends with a question mark, so that is not a statement. Okay? So, no. Man, that hurts. That's not a statement. A man, that hurts is an exclamation. So once again, that is a no. 432 plus 8 divided by 1.3 is equal to the square root of 115,000. Well, little do people know that when you actually draw an equal sign, you're actually making a statement. Because you're saying this A equals B is what you're saying. So because it has the equal sign in there, this actually is a statement. So yes, it is a statement. This book is about database management. That's either true or that is false. So that is, yes, a statement. Watching reality shows turns your brains into mush. That is I'm just joking. No, that's not a statement. That is an opinion. Okay? Because we cannot verify whether it turns your brain to mush or not. Okay? So that is a no. That is a opinion. Opinions are not statements. So when someone gives you their opinion on something, they're not making a statement. And so you can tell them, we can't, like, that's not even using sound logic to make an opinion, right? You got to first start with factual statements, okay? Things that are either true or false. Okay? So, simple and compound statements. Statements can either be simple or compound. A simple statement contains only one idea. So each of these is a compound statement. Your jeans are torn. My dorm room has a pile of dirty socks. And Daytona Beach is in Florida. All these are phrases, sentences that can either be true or false, but not both. But statements like, I'm taking chemistry this year and I'm going to get an A is a compound statement because it has two statements in there, right? So a compound statement is a statement formed by joining two or more simple statements with a connective. And the connectives are, in logic are the word and, which is a conjunction, the word or, which is a disjunction, and if then, so that means a condition, like if you give me $500, then I'll take you to the movies, okay? Like, that's a conditional statement, all right? The if then is called conditional. And if and only if is a biconditional, which means both of them necessarily have to be true, right? So, I'm a man if and only if I have the XY chromosomes, right? So I'm a male if and only if I have the XY chromosomes. That's a biconditional statement, right? Either both are true or both are false, but one can't be true and one can't be false. Okay, so there's that. All right, so here are some examples of compound statements using connectives. John studied for 5 hours and he got an A. That's a conjunction, right? Because he has the word and in there. I'm going to pass this class, or I'm going to change my major. So that is a disjunction because it has the or connective in there. If I get 80% questions right on the LSAT, then I'll get into law school. That's a conditional. If, then. If blah, 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 then blah, blah, blah. And a biconditional. We will win the game if and only if we score more points than the other team, right? So, like, they're both, one follows necessarily from the other, right? If both of those aren't true, then none of them are true, okay? Because you can't win a game if you don't score more points than the other team, unless you're in golf. All right, so example. Classify each statement as a simple or compound. If it is compound, state the name of the connective used. So, first one. Our school mascot is a moose. Okay, that's a simple statement. There's no connectives in there. So that is a simple statement. All right. B. If you register for Wi-Fi service, you'll get 3 days of free access. So that is an if-then statement. Even though you don't see the then, it's implied. You're making an implication. If blah, 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 you know, another blah, blah, blah will happen, right? So this is a conditional. Because if dot, 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 then. Okay. C. Tomorrow's the last day to register for classes. I think that's just a simple statement, right? It's either true or it's false. Okay. In the interest of saving the planet, I plan to either buy a hybrid or a motorcycle. So that is an or compound statement, right? So that is a disjunction. Okay? Good. Okay, so there's that. So now we want to talk about quantified statements. So quantified statements involve terms such as all, each, every, no, none, some, there exists, and at least one. The first 5, all, each, every, no, and none, are called universal quantifiers because they either include or exclude every element of the universal set. So if you're noticing something, you're seeing these words, universal set, you know, the set of things, right? Logic and set theory are essentially the same thing, just like they're two halves in the same coin. So if you like set theory, you know, then logic is nothing to be afraid of. If you like logic, set theory is nothing to be afraid of. So there's an if and only if there, right? If you like set theory, if and only if you like logic. Okay? So there's that. That's not true, but still. So some examples of quantified statements. Every student taking philosophy this semester will pass. Hopefully that's true with your philosophy class. No nursing student is majoring in criminal justice, right? Some people who are Miami fans are also Miami Dolphin fans. Miami Hurricane fans are also Miami Dolphin fans. There is at least one professor in the school who does not have brown eyes. Okay? So those are some examples of quantifiers. Those are just like the words every, no, none, some, there exists, right? And the word there exists means like there's at least one. And sometimes the word some also means there exists at least one. Okay? So now we're going to learn how to transform statements into the opposite of what they mean. And this is negation. So negation of a statement means that it has the opposite truth value. So if something was true originally, the negation of it will make it false. Okay? So if a statement was true, negating it will make it false, and vice versa. That means that if a statement is true, its negation is false, blah, blah, blah. So for example, if the statement, my dorm room is blue, what's the negation of that? Well, it would be, my dorm room is not blue. Okay? It's important that the truth values of these two are completely opposite. One is true, the other is false, period. You can't negate my dorm room is blue and say my dorm room is yellow, because it's completely possible that both statements are false. Okay? Your dorm room can be your dorm room can be red, and then it's not blue, or it's not yellow either. Okay? So when you say, when you're negating something, you have to put the not in there. Okay? You have to make sure that you are saying the opposite of what you mean. So here's a statement. Auburn will win Saturday. The negation of that will be Auburn will not win Saturday. I took a shower today. The negation of that is I did not take a shower today. My car is clean. The negation of that is my car is not clean. So I think we get the idea there, right? You always want to say the opposite, okay? So you have to be especially careful when negating quantified statements. Quantifiers, they don't follow the rules you think that they should, all right? At least not for the English language. So here's my biggest thing with logic, okay? Do not try to make it make sense grammatically. Your sentences and logic might sound weird, all right? Especially when you negate them. That's okay. Something can sound awkward with English, but still be valid logically. So just because something sounds weird doesn't mean that you're wrong, okay? You might actually be 100% correct. So for example, so consider the statement, all dogs are fuzzy. It's not right to say that the negation is all dogs are not fuzzy, all right? Because if some dogs are fuzzy and others aren't, then both statements are false, okay? So let's think about that for a second. All dogs are fuzzy. We can't say all dogs are not fuzzy, all right? Because if no dogs are fuzzy in there, then both of those statements are false. Remember, we want one truth value to be true and the other one to be false. Okay, we don't want we don't want there to be a universe where both of them are false. Okay, so how do we negate that? The negation of all dogs are fuzzy is that some dogs are not fuzzy. Okay, some dogs are not fuzzy. In this setting, we define the word some to mean at least one. Okay, so negating all, right, means that there's at least one. Okay, so because it's true that either all dogs are fuzzy is true, right? So picture a room of all fuzzy dogs, right? If I want to negate that, the negation of it is not that all dogs are like bald, okay? Because there could be a world where there's like one dog that is fuzzy. Instead, we want to say, okay, all dogs are fuzzy. That's true. The negation of that would be like, well, there's at least, one dog that is not fuzzy, okay? All the dogs could be fuzzy except one. One dog could be bald, okay? And then, therefore, that completely negates my statement, all dogs are fuzzy, all right? I hope that makes sense. So, if we see all, the negation is some, okay? Some do not, or not all do. If we see the word some, the negation of that is none, okay? So to negate all, you say some. To negate some, you say none. To negate some do not, you want to say all do. To negate none, you want to say some do. All right? So that's how we do our negations, so we have to be very careful with them. So let's seeing how much time I have. So let's do a negation of this. Negate the following quantified statements. So every student taking philosophy will pass. I have to find it. So this has every, right, which means all. All right. So we're trying to negate all. What's the negation of all? Well, the negation of every is not every, right? Or the negation of all is some. So for A, we would say not every student taking philosophy will pass. All right. And in case of the word all, you could say or. You could say some students taking philosophy will pass. Okay? So, that's good. B. Some students who are Miami Hurricane fans are also Miami Dolphin fans. So what's the negation of some? From the last slide, it was none. So no people who are Miami Dolphin fans, sorry, Miami Hurricane, are also Miami Dolphin fans. Okay? C. There's at least one professor in the school who does not have brown eyes. Okay? So, the negation of there is at least one would be all. Okay? This says the negation of that would be all professors in this school have brown eyes. Brown eyes. Okay? D. No nursing student who is majoring, nursing student is also majoring in criminal justice. The negation of that is not all, but at least one. So, or some. So at least, or some. So at least one or some nursing student is majoring in criminal justice. Okay? So, that's how you negate. Okay? So, after we negate, we want to learn how to put our phrases, our statements, into symbolic language. And we want to be able to put them in symbolic language because that helps us once again strip away the emotion. Okay? And just look at objective facts. So, where is it at? It's right here. So, our main goal in formal logic is to be able to evaluate logical statements objectively. In order to do that, we'll need to write our own statements in symbolic form. So now we introduce symbols and methods that will be used. So, and, its symbol is like this upwards caret, okay? Or, it's this downwards caret, like a V. If then, it's an arrow, all right? So, P implies Q, you draw an arrow. P, arrow, Q. If and only if is called a biconditional. So, simple statements in logic are usually denoted with lowercase letters like P, Q, and R. For example, we could use P to represent I get paid Friday, and Q to represent the statement I will go out this weekend. And then the conditional statement, if I get paid Friday, then I will go out this weekend, can be written as P implies Q. P arrow Q. The symbol tilde, like that little curvy thing, represents the negation. So if P still represents I get paid on Friday, then I'm going to call that not P. Not P represents I do not get paid Friday. All right? So, logic It is fun. So let P represent the statement, large coney is a dog. This is from the book. And Q represent the statement, Guinness is a cat. All right. What does not P and Q mean? So that's how you'd say that. Not P and Q. So if P is large coney is a dog, then not P is large coney is not a dog, right? So not P and Q would be the compound statement. Large coney is not a dog, and because the and symbol here, and Guinness is a cat. All right. And so then we have this not P and Q. So not parentheses P and Q. So what does P and Q mean? P and Q in this case would be large coney is a dog and Guinness is a cat. So not P and Q would be us saying it is not the case that large coney is a dog and Guinness is a cat. Because we're negating that whole phrase. Do these say the same thing? So we have, let me make it blue. So we have this and we have this. Do these say the same thing? Well, let's look at this. Large coney is not a dog and Guinness is a cat. Okay. It's not the case that large coney is a dog and Guinness is a cat. So this is saying that, so both of these say that Guinness is not a dog. Okay, so that's good. However, this says Guinness is a cat, but this says Guinness is not a cat. So these do not say the same thing. So once again, these parentheses matter. All right, they matter. So they do not say the same thing. Okay. So the next slide. Let P represent the statement, it is cloudy, and Q represent the statement, I will go to the beach. So we want to be able to write these phrases in symbols. So P says it is cloudy, and Q says I'll go to the beach. So if I say I will not go to the beach, I'm writing the negation of Q. So I would say here, if I can write it, yes, not Q. Not Q, because I'm saying the opposite of Q. It is cloudy and I will go to the beach. So I'm saying, I'm making the statement, it is cloudy, so that's P. I'm saying, and I will go to the beach. So that is P and Q in symbols. If it is cloudy, then I will go to the beach. So you're saying if P, then Q. So that means that P implies Q. If P, then Q. And I will go to the beach if and only if it is not cloudy. So this is saying I will go to the beach, P, if and only if, which is the biconditional, it's the double arrow, if and only if it is not cloudy, which is the negation of Q. Okay? So once again, this says, you probably noticed that some of the compound statements we've been writing have been sounding a little awkward. And it isn't always necessary to repeat the subject and verb of the statement using and or. For example, the statement, it is cold and it is snowing, can be written as it is cold and snowing. Okay? So use that at your leisure. But just make sure that your logic is correct. Okay? Don't shorthand it so much that I can't understand your logic. Sometimes writing out more things with logic statements is actually useful. All right. So, this last one. So write each statement in words. Let P be my dog is a golden retriever and Q be my dog is fuzzy. So A here says not P. So P is my dog is a golden retriever. So not P is my dog is not a golden retriever. I'll just write GR for golden retriever. B, we have P or Q. So this says my dog is a golden retriever or my dog is fuzzy. Okay. C, not P implies Q. So this is if my dog, you always want to say the if first. If my dog is not a golden retriever, then Q. What's Q? My dog is fuzzy. So this is just us learning how to write these things out, right? D. P if and only if Q. Q if and only if P. So my dog is a golden retriever if and only if. Sometimes you might see this IFF. That means if and only if. You're allowed to use that if you want. Okay. If and only if. My dog is golden retriever. Okay. All right. E. Q and P. So Q is my dog is fuzzy. So my dog is fuzzy. And my dog is a golden retriever. So you can say my dog is fuzzy and a golden retriever. Okay. So that's good. Sweet. So that is the first section down. So I'm actually going to go ahead and cut this off. That way I can make the next video all about the singular topic that we're going to talk about, which is truth tables. All right. So I'm going to break these videos up. They'll be on my YouTube. So I will see you all then.